So has everybody gone out and tried to? Okay, everybody has to click that they can leave the room, or you can stay on and be recorded. I think the videos on YouTube kind of go through unscathed, so that works pretty well. And I see a few of you have visited the page. And if you want to make me feel good, click the little thumbs up thing, okay? And I know you are the only ones in the whole world that are going to watch it. I don't think anybody's going to sign on and watch these lectures for entertainment, but you never know. Okay, let's go ahead and let's get started. We're talking about multidimensional signal processing, and we've talked a lot about multidimensional signals, and we've been going through some of the theorems. So let me go ahead, and I have to close one of my computers. Okay, there we go. I have to close one of my screens, and I will go ahead and I will share my screen, and we will go ahead and get started. Okay, the last time, let's kind of review. We had the multidimensional Fourier transform, which is beautifully compressed. I think whoever came up with this notation is just really, really smart for a multidimensional Fourier transform. So this is t as a vector and u as a vector, and yeah, if you have n time axes, n axes in n dimensions, then you're going to have n axes in also in the frequency domain. So this is the expression for it. This is the shorthand notation, the xt double arrow into x of u, where u is the frequency domain. And here is the relationship for the shorthand notation. The integral over t is equal to these integrals, and the differential is equal to the product of all the individual one-dimensional dt's. So we've gone through that. And then this is an example of writing it out. So maybe sometimes, okay, what's wrong with my marker here? Okay, I guess I'll just have to go this way, except I can't go this way because I'm going to need to point out later what's going on. Huh, I wonder why it isn't working. It's worked so well before. Excuse me, guys. I'm going to go check one thing in my connection, and then I'll be right back. So please excuse me for just a second. Okay. Nope, no better. Okay, one more try here. Yes. Oh yes. Oh yes. I did the Microsoft check. I unplugged it and plugged it back in, and miraculously, it's working now. Okay, so on the bottom here, on the bottom is the two-dimensional Fourier transform. If we were to write it out in longhand, so instead of a vector t, we write t1, t2, and instead of writing these vector products as the transpose of the frequency times time, we just write it out, u1 t1 plus u2 t2. And so you can see how this Fourier transform would unfold if we wrote it out in longhand. And that's the purpose of doing it. That's the purpose of the shorthand. It's such a beautiful, compact notation to generalize us to higher dimensions. These are some of the Fourier transforms. Last time we talked about the transform definition. We have not talked about linearity, but I think that's almost trivial. That the sum of the transforms is equal to the transform of the sums. That's the additivity criterion. And if you multiply or amplify a signal by 7, you amplify the Fourier transform of the signal also by 7. This is the inversion formula, and the inversion formula also has a beauty associated with it that we see in the one-dimensional Fourier transform case. In the forward transform, we use e to the minus j. That's in the forward transform. In the inverse Fourier transform, we use e to the plus j. So it's the same convention that we used in the one-dimensional case. And what we're trying to do here, I hope you notice, is we're trying to adopt a notation so that the notation doesn't get in our way, so that we have a very nice, beautiful representation of these signals and their Fourier transforms in order to allow us to think more about their properties than the bookkeeping of keeping track of where the 2 pi's go through and things of that sort. We talked about this last time. We'll go through that very quickly again. This is the Shift Theorem. We're going to go through now the Separability Theorem. Now, up to this point, everything, at least these 4 theorems, is a straightforward generalization of the one-dimensional counterpart. That is, all of these theorems have a one-dimensional Fourier transform associated with them. At least the notation. Now we're going to get into some more interesting things that happen in higher dimensions that do not happen in one dimension. One is separability. We will talk about that today. Rotation, scale, and transposition, we'll talk about that. I think we'll get to convolution today also. Convolution is a straightforward generalization insofar as the math goes, but I also want to go through the geometry of two-dimensional convolution. And lastly, we have the modulation theorem. The modulation theorem is the dual of the convolution theorem. So you convolve in one domain and you multiply in the other domain. So the Fourier dual of that is you multiply in the time domain and you convolve in the U domain. By the way, I will be referring to T as the time domain. You do not have multidimensional time, so we can think of even T1 and T2 as being spatial variables. I don't know what happened there. It looks like a comet got launched. So we can think of a two-dimensional picture. Here's a little picture of a guy. Right, a two-dimensional picture is T1 and T2 are not time anymore. They're spatial variables. They're X and Y, if you will. Or if this was a digital image in discrete time, this would be an N1 and an N2. So I'll refer to the T with the vector over it as time, but you can see that it generalizes to spatial dimensions or anything that you want to. In fact, you can mix and match. You can have X as a spatial dimension and T as a time variable, okay? And you could have two-dimensional functions where the variables are mixed and the 2 variables don't even have to have the same dimension. This is certainly something which is allowed with what we're doing. So with that, let's go on to the next slide. This was the shift that we talked about. I won't elaborate on this very much, except to say that this is what we looked at last time. And this is the proof that we went through last time. And we won't go through this again. So let's, but the basic idea, the final result is if you shift in one domain, you all multiply by e to the j in the other domain. Just exactly as we do with the, one-dimensional Fourier transform counterpart. Let's talk about convolution. Now, convolution, what is convolution in terms of multidimensional signals? Well, it's exactly the same as the one-dimensional counterpart, except that we're using vectors instead of scalars. And what I want to do is, first of all, prove this theorem to you. And the proof is relatively straightforward. It's just like the one-dimensional case. And then give you an example of what happens in higher dimensions by drawing some pictures. You can see, for example, that the shift is a little bit different in two and three dimensions than it is in one dimension. One dimension, we think about moving back and forth, right? In two dimensions, we think of shifting an entire object to another point on the plane, or in three dimensions of shifting an object to a point in space. So we need to spend a little bit of time in terms of interpreting that. So here is the definition. We're going to start with the Fourier transform of y of t. This is the Fourier transform of y of t, right? This is the same y of t that's up here. And now we're going to simply take the definition of y of t and we're going to substitute it into this integration. The next thing we do, always in these proofs, there's just a few things that's done. One is change of variables. The other one is variable substitution, and the other one is switching around integration limits. So in this one, the next thing we're going to do is we're going to switch around integration limits. So we switch around integration limits. We bring the t integral inside, and we bring the tau integral outside. And then in the nested integral in here, we just put everything that's a function of t, everything that is a function of t. And then everything that's not a function of t, we put outside the square brackets, and that's the function of tau on the integration. Now here's where we can apply something that we've seen before. What is this? This is a Fourier transform of a shifted function, right? This is a Fourier transform of a shifted function. So the thing in the square brackets can be analyzed using the shift theorem. We could go ahead and do the variable substitution, yada, yada, yada. But in the end, we would just be rederiving the shift theorem. We don't want to do that. I see everybody is still writing down, so I'll give you a second while I avail myself of a refreshing beverage. By the way, I would remind you that all of these slides are downloadable in the Google Sheet. I give you a link to that. They're all in Box and are accessible, are inaccessible. No, they're accessible. They're accessible in Box for you if you'd like to download these slides. And by the way, you'll see that I update these slides every once in a while. So don't download a collection of slides and assume that they'll never change again, because I'm going to add on to them as different lectures come on. So again, we're down to this point after we've shifted integration operations, and the nested integral can be evaluated using the shift theorem. And what happens with the shift theorem? We get the Fourier transform times an e to the minus j shift, right? So that's what we get here. So we get the original function down here, and all of the stuff in the square brackets just becomes the Fourier transforms times e to the j shift, right? And now it's beautiful. We can take this transfer function outside the integral sign, because we're integrating with respect to tau, and that's not a function of tau, so we can take it outside the integral sign. And once we do that, what do we have left? What we have left is the Fourier transform of x. What we have left is the Fourier transform of x. So again, we've taken this h sub u outside of the integral sign, and this is what is left, and what is left is recognized as the Fourier transform of x. So we see that just as in the case of one dimension, a convolution will Fourier transform to y of u is equal to the Fourier transform of x times the Fourier transform of h. So that's the convolution theorem. Again, straightforward generalization to the one-dimensional counterpart. You're going to hear me say the word counterpart a lot. Now, what I'd like to do is I'd like to go into the mechanics of two-dimensional convolution, because I think what you see it, you'll go, oh yeah, this is exactly what happens. And by the way, you've probably heard of convolutional neural networks. Anybody heard of convolutional neural networks? Okay, so people have heard of convolutional neural networks, and it turns out they're not, they're misnamed. They're not convolution, they're correlation neural networks, but they were misnamed and the name has stuck with them. But this will give you an idea of what to do in convolutional sort of operations. So this is the convolution, but it's written out in longhand. So we have both the integration signs here. Here's a two-dimensional function, and here's our shifted h. So with that in mind, let's go ahead and start with some shapes. Now, in order to geometrically interpret here, what we're going to do is we're going to assume a two-dimensional function, and if you want to get technical, this function is 1 inside the shaded area and 0 outside. It's 1 inside the shaded area and 0 on the outside. And so we want to perform a two-dimensional convolution of this function x with this function h. So these are two two-dimensional functions that we would like to perform a convolution of. Now, what we're going to do in order to perform that convolution is we're going to pay attention to exactly what this integral is, especially of this t1 minus tau. First of all, you'll notice that we're integrating with respect to tau, correct? We're integrating with respect to tau in the convolution. So the first thing I'm going to do is I'm going to take this h of t1 and t2 and say, let's make it a function of tau1 and tau2, right? It's kind of like a dummy variable, and call this h of tau1 minus tau2. Then I'm going to take of h of tau1 minus t1. Now, what does that mean? Well, in this sense, t1 is a fixed number and t2 is a fixed number. And so what this is going to do is take this two-dimensional function as a function of tau, and it's going to shift it to be equal to be centered, the new origin is at the points t1 and t2. This is exactly what we saw with that shifted square. And for reasons which are clear to me, some people don't think you need to do this, but let's take a look at, let's take a look at this and let's call it something. Let's just call this function a k of t1 and t2. I'm just going to redefine a function. The reason I'm going to redefine a function is the next step, because it allows me to look at the transposition of this k. And now I'm going to, I'm sorry, boy, this is screwed up. This should be a T1 and a T2. So what this k of minus T1 and T2 is a transposition of this k, which means that I reverse the T1 axis and I reverse the T2 axis. So it's exactly like flipping it around this way and then flipping it around this way, flipping it around horizontally and then flipping the function around vertically. And this becomes the k minus t1. So from getting from here to here, I just like to think of the k of t1, t2. And I understand this transposition. But the way that it goes, if we let the h's tag along, this is equivalent to taking the arguments of this h function and multiplying by -1. So this is in fact the h of t1 minus, or t1 minus tau 1, t2 minus tau 2. And what's my motivation there? My motivation is to duplicate this kernel in the convolution integral. I want to duplicate this kernel in the convolution integral. And notice I've done exactly that. So if we want to find out the value of the output at T1, T2, now notice, this is the value of the output at this point. The value of the output at that point is equal to x times this h. In other words, we multiply this x times this h, and since this is a binary function, that is 1 and 0, the product is just going to be 1 inside the black area here. Is that okay? And so that's that area in the black is going to be equal to the value of the output at the point T1, T2. Whatever that area is. And I want you to notice as T1 and T2 vary, what's going to happen to this triangle? It's going to shift around, isn't it? It's begun to shift around the two-dimensional plane. And if you remember in one dimension, what was the little rule for convolution? Remember flip and shift, right? That's exactly what we're doing. We're flipping here, except we're flipping in 2 dimensions. Flip horizontally, flip vertically. Flip, and then we shift around and look at the overlap. And we have to look at the overlap for all values of the shift. And if we look at the values of all the shift, we can see that we're going to be able to generate the output, which is y. And we have to, for every different shift, we get a different value of the output for the T1 and T2. We shift to another value of T1 and T2, we get another output at T1 and T2. So we fill up this plane. So this is the basic idea of convolution. Now there's plenty of places which, where'd he go there? Okay. There's plenty of places where convolution is used. Let me get a blank screen here to look here.
Dr. Marks?
Yes.
I have a question.
Yes, okay.
So on 6,
yes.
So when you're moving that around,
moving the triangle around, yes.
Yeah, so I think I might be confused because the way I see it, for all values of T1 and T2, like you're going to get the entire circle, aren't you?
There will be. It looks like there are values of T1 and T2 where the triangle is totally going to be subsumed or included in the oval. Yes.
Yeah. Okay.
And so there will be a point that the value doesn't change for little wiggles in T1 and T2. And okay, clearly, and then what happens if T1 and T2 are too big? There's no overlap. There's no overlap. Right? Yeah. So it's 0. So you can see go ahead.
So when you do that, so let's say for a certain set of values for T1 and T2, you get the value of the circle function or oval function at 0, 0. And let's say you get that for like 2 different sets of T1 and T2. If this is just a binary function.
No, it isn't. Just, the original function is binary, but the convolution is not.
Okay, so you will add up a bunch of 1s as you start to add up more parts of the oval function. Okay.
basically it's going to be flat in an area, and then it's going to taper off to 0.
Okay.
So the convolution itself is not binary. It's not
Okay.
just 0 and 1. We chose the binary because it's easy to draw pictures of.
Okay. Yeah. Got
Okay.
it. Thank you.
Okay. Any other questions? Okay. Let me get rid of this other stuff here. This is premature. We used to have cases in something called a scanning densitometer. Okay, I don't know how to spell it from now on, but the basic idea is as follows. You have an image, and for example, this image is just for purposes of illustration, is backlit by a light. Okay, so there's a light back here. And there's a picture here. And you want to capture this picture. This was in the days before. This was in the days before, digital photography and stuff. You want to scan, you want to get this. So what you would do is you would take a photo detector, and here's the photo detector. And this photo detector only gives you a single value out of it. What it gives you is the total amount of light that's incident on the photo detector. Does that make sense? And what one does is you would move this photo detector up and down the image, and you would capture this result. So if you were over here, for example, with the photo detector, what would you get? Well, you would get whatever the gray level was for all of the values within the photo detector. Does that make sense? And you would move this photo detector around almost like a raster, and you would capture the two-dimensional readings from the photo detector in order to try to capture the image. The problem is that the photo detector is too large to catch a lot of the detail, right? That photo detector is big with respect to some of the detail that is in the image. And so what happens is that the result that you get out, can you see what happens here? This is exactly what happens with convolution, isn't it? This is exactly what happens with convolution. You're going to get out the original picture, and I don't think I can draw the original picture here, but you're going to get out the picture, but it's going to be degraded. It's going to be convolved with a little circle. This little circle is the area of the photo detector. You're going to get out something which with much lower resolution. And so that's the way it's going to work. Now, today on a CCD array, for example, imagine that instead of a photo detector, we have a bunch of CCDs. And we're trying to capture an image. Forgot this poor guy's ears up here. Now, what does the CCD do? The CCD does the same thing. It takes whatever light is incident upon the CCD, and it gives you out one number, right? It gives you out a number for this it gives you for this photo detector. It gives you out a number for this photo detector, right? But you notice it has a similar effect as this original one. Well, this turns out to be equal to the original image convolved with a rectangle, except that the rectangle is not, this is not going to be a continuous signal, isn't it? This is not going to be a continuous signal. But imagine this rectangle moving around as in a convolutional sense. So you get this rectangle moving around in a convolutional sense. So it begins to explore and do all the convolutional things, except we don't save all of the values. We only save the values where the rectangle overlaps a pixel. So we can think of convolving this with a rectangle and then sampling it. And so what I'm hoping you see here is two relatively intuitive ideas of where convolution occurs in everyday life. And I do know I did some consulting for a company called Neopath that took digital images. And I think you can see that this becomes less and less of a problem when the pixel size gets smaller and smaller, right? But as the pixel size gets larger and larger, you get more smearing. So they literally took this value, recognized it was a sample, that this convolution degraded the integral, or degraded the image, and put in a restoration to restore the original pixel value. So this is something which has been used in image processing. Is that okay? This is very interesting. The other thing is that another place that it's used, if you take Dr. Schubert's class, for example, and if you take Dr. Schubert's class, here's another example of what goes on there. Suppose you have a nice image. And this is a nice smooth image of a picture. And you want to catch the areas in the image where there are edges. You want to catch just the edges. What you would do at any point to get the edges, if any of you taken Dr. Schubert's class in image processing at all? Okay, so Glauco could maybe help me. You take this point and you say, okay, if I want to get my vertical edges, what I'm going to do is I'm going to look at, I'm going to do a 3 by 3 pixel. And I'm going to put, do you remember the Sodal operator, Glauco?
Yes, this is familiar to me.
Okay, do you know what the numbers are?
For horizontal line?
Oh no, for any Sodal operation.
I don't, for what kind of operation? Sorry.
Okay, I should have been more prepared for this. I believe it's called Sodal. Let's go to the source of all knowledge, which we have at our fingertips.
I'm not familiar with that. It's the first
Okay.
time I listen it.
By the way, I'm using DuckDuckGo. Yeah, here's a Sodal operator, for example. Okay, does everybody see this? This is Sobel, S-O-B-E-L. A Sobel operator. Do you see this operation? This operation is for a horizontal edge. What you do is you multiply this pixel by 1, this pixel by 2, this one by 1, the middle one's by 0, and the other one's by the minus. What are you going to be detecting here as this thing moves around the image? You're going to be detecting horizontal edges. You're going to be detecting horizontal edges. So if we go over here, and I'm afraid I'm going to lose it 1, 2, 1. say, for example, in a part of the picture, you had an edge, and the edge was totally black in here. So it was equal to 0 in here, and it was equal to 1 in here, or 200. Well, I'm doing the grayscale image instead of the byte image. Now, if you put this kernel at this point, and this was totally white, in other words, there was no changing, what would you get out?
The same thing.
You get out, no, you get out 0. Because it would take the value of the pixel here, here, and here, and subtract the pixels of here, here, and here. And if all those pixels were the same, you get out 0, wouldn't you? Even if this was a gray area, you get out 0. Even if this was a gray area, that you get out 0. So what if you put it down here? If you put it down here, you'd still get out 0, wouldn't you?
Oh, so on the top you get out 0 because of the integration part.
Yes. Oh, okay. I should say yes. You sum the products.
Yeah. Okay, that makes sense.
You
And on the
sum-
bottom you get 0 because of multiplication.
Well, you also sum the products here.
Yeah.
But
yeah, okay.
since all of the elements are exactly the same, so when are you going to get a difference? You're going to get a difference when this operator is across an edge, aren't you? When this operator is across an edge, you get a difference. And so what will happen then is once you apply this Sobel operator, what you will get out ideally is just the edge of the difference between the two values. So it's an edge detector. So you can see this is another example of this is truly correlation, but it's kind of a convolution, right? Because we're doing the shifting all around, and we're multiplying everywhere by this result, and we get an edge detector. So there's different Sobel operators for different detection. If you're doing image processing, you have a Sobel operator that catches the horizontal, the vertical, and you have another Sobel operator that catches all of the edges. And so that is another example of the two-dimensional convolution. So I mentioned that hopefully to get you to see some kind of everyday applications of convolution as we do the two convolution.
Dr. Mars.
Yes.
So this grid that you have here, does each like box represent just one individual value of T1 and T2?
Yes, this is not a T1, this is discrete. So these are pixel values. This is N1 and N2. So it's
Okay.
a digital. So we don't shift continuously. We shift by the next pixels, the next pixels, the next pixels. So we're not doing a continuous sweep, but this is the digital equivalent of two-dimensional convolution. Exactly the same sort of mathematics. Let's go back here and ask ourselves, we really haven't addressed this, but in 2 dimensions, what does a high frequency look like? High frequency looks like, well, one of the places it looks like, if you did a sinusoid, it'd be a bunch of very closely spaced lines, right? Like this would have a higher frequency, closely placed lines, as would, for example, lines that were spaced further apart. This has a higher frequency. In fact, sometimes in optics, they don't talk about cycles per meter, they talk about lines per millimeter. So that's a frequency component. So does that make sense that this is a high frequency component? What happens if you put this high frequency component over the scanning densitometer or the Sobel operator? What happens? It's going to be wiped out, isn't it? You're going to get a smearing of the high frequencies. And this is exactly what happens in aliasing. You smear the high frequencies. You're not sampling the thing fast enough. Where if you have lower frequency components, you're going to be able to capture everything. So ideally, what is your scanning densitometer going to be? It's going to be a single point, isn't it? Right? But the problem is, in practice, you can't have it a single point because that's just too small. You have to have it a finite size. And to do edge detection, you need to figure out what you need to figure out what how many elements you have to do in order to grab an edge. And 3 by 3 is a very typical number that you use. And this gets into philosophical questions, and we'll talk about this probably later in the course if we have time. But if you have a sinusoid and you ask yourself, what is the frequency here? This is the only point you know in the signal. Is there anything you could tell me about the frequency of this sinusoid? No, it isn't enough information, is it? You need a bunch of wiggles. You need a bunch of wiggles in order to tell you what the sinusoid is. So we get in this idea, and there's literally philosophical questions of what is instantaneous frequency. Instantaneous frequency can be argued not to exist because the frequency at a point doesn't exist. You need the context of the frequency around it, don't you? And the more wiggles you have around that context, the better you're going to know the frequency. So anyway, I'm getting a little off topic here. But these hopefully, again, are examples which gives you an intuitive idea of some of the ideas of application of two-dimensional convolution. Now, in the examples that I gave you, there's no flip, but there's shift. And when you just shift, that's correlation. But when you flip and shift, that's convolution. So both of them are shifting sort of operations. So we get back to here and we see what happens in this geometrical interpretation of two-dimensional convolution. And I think you can see what happens in three-dimensional convolution. You have this three-dimensional object and you have the other object you're convolving with, and you have to shift it to every point and multiply the two together and get the area of the overlap, and that's the mechanics you visualize in order to do that. Of course, as an undergraduate, they have you do a bunch of flip and shifts, and you get really good at convolution. And then somebody comes and tells you, "Hey, you don't know, you don't have to flip and shift. You just take the Fourier transform of the two, and you inverse Fourier transform, and boom, there's the convolution." And so often, it's easier to do the Fourier transforms, and then invert Fourier transform as opposed to doing the literal flip and shift. Okay. One other thing, I should probably mention a few other things about Fourier transforms. Fourier transforms are ubiquitous. They occur in nature. And those of you that have done any works in antennas will appreciate the following. If you take an antenna aperture, say this is a square aperture, then the physics of the far field this is a T1 and a T2. And so this is X of T1, T2. What happens in the far field is the Fourier transform. You get something akin to big X. And if you've ever done things like phased array or far field, either in radar or sonar, you know that God has designed the universe so that just the act of propagation generally generates a two-dimensional Fourier transform. That's really astonishing that nature works out that way. Now, it isn't exactly the Fourier transform. Clearly, as you get further and further from the source, the far field, the image begins to get bigger. But it gets to a point where it's a Fourier transform, and if you go out a little bit longer, then it's a Fourier transform, except the Fourier transform is magnified. And so the Fourier transform just gets bigger and bigger and bigger and bigger after a point. So this is something which is done in 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 optics. And that's one of the incredible things about optics is that, yeah, we have this idea of the Fourier transform occurring very, very naturally. Fourier transform, I think I mentioned in the beginning, I believe that probably the integral equations are probably the first, or I'm sorry, differential equations. Differential equations are probably the most used of the mathematical tools. I think the Fourier analysis and Fourier transforms are probably the second most. At least that's true in my experience. You're going to have people argue with you, but that's okay. So any questions, any additional questions on this? If not, let's go to separability. Separability is something that does not happen in separability does not happen in one dimension. Now, what does separability mean? It means that the function can be written as the product of two functions, like pi of t1 times pi of t2. This is a separable function because the function with respect to t1 is totally separate from the function of t2. They're separable functions. We could also have something like pi of t1. They don't have to be the same function times the sinc of t2. Pi of t1 times the sinc of t2. This is separable also because it's two one-dimensional functions which are multiplied together. Let me tell you how I like to think of one-dimensional functions in two dimensions. Whoops, t2. What if I had the function of pi of t, which is the rectangle function? And what I wanted to do is I wanted to take this rectangle function, this one-dimensional function, and I wanted to represent it as pi of t1. In other words, pi of t1 is equal to my two-dimensional function. But my second variable doesn't appear explicitly here. Does that make sense? How do you think of a one-dimensional function in two dimensions? How do you think of a one-dimensional function in two dimensions? Well, it's very interesting. This means that whatever x of t1 and t2 is, it's totally independent of t2, right? And so we can think of this function, first of all, here, this is a rectangle function. Imagine this coming out and being 1 here at the 1 on this little strip here. Well, it's also 1 on this little strip, 1 on this little strip. And so it turns out to be a slab, if you will, going from -1/2 to 1/2 without the curly edges. But it's something which is 1 inside the slab and it's 0 outside the slab. That's how pi of t1 would be plotted in two dimensions. It's not a function of t2, because no matter where you go at t2, it's exactly the same. And I like to think about this as follows. If you kind of look at me, I would think of it as a one-dimensional function, and you take this function and you smear it down the axis. So you're taking this rectangle function and you're smearing it down the t2 axis. And that's the one-dimensional function. So we can, for example, think of something such as pi of t1 times t2. And pi of t1 times t2 is a separable function. And so pi of t1 we've decided is equal to 1 inside these intervals. Boy, that's a terrible job. Okay, let me try to do this. This is pi of t1, right? And this is pi of t2. I haven't labeled my axes here, t2, t1. And this is pi of t2. And I think you can see the only place that one or the other functions is not zero is in this intersection, right? So the separable function pi of t1 times pi of t2 looks like a little pillbox centered around the origin. And it's a separable function. Why is it separable? Because it can be written as the product of a function smeared one way times the product of another function smeared another way. Okay? Now there is a theory. Let's see if I can grab another screen here. It kind of sounds like if you have a separable function, then you're going to have kind of a rectangular structure, right? Because you have one thing smeared this way and one thing smeared the other way. So it kind of looks like you might have a rectangular sort of structure in whatever the periodic function is. But indeed, that isn't the case. Consider, for example, the function x of t1, t2. This is going to be a separable function, as equal to e to the minus t1 squared times e to the minus t2 squared. This is a very nice separable function, correct? But notice this is the same thing as a function of e to the minus r squared, where r is the polar coordinate, right? On the t1, t2 plane. So this literally has, if we were to look at a contour plot, and hopefully you all know what a contour plot, the contour plot of this function would be a bunch of circles. Wouldn't it? Right? I don't know if I can draw it from the side, but it would look like a gumdrop, right? So it would have these contour circles where this is t1, t2, and this would be x of t1, t2. So we can indeed have separable functions. We can indeed have separable functions which do not have a rectangular kind of blocky sort of structure. We can have rectangular functions. There's a fascinating, this is a little side note here, a little historical side note. If you're familiar with probability, you remember probability said that if two random variables were independent, then those two independent random variables could be expressed as the product of the one-dimensional probability density functions. Do you recall that? Independence takes two-dimensional probability functions and separates them into two. So if we had 3 dimensions, for example, we were to look at the probability density function for 3 samples. It would be x of t1. This is some history. X of t2, x of t3, right? So this is something, if the x's are probability density functions. If you don't remember this, that's okay. If you do remember this, you'll be impressed. Okay, so these are probability density functions. Well, imagine the velocity distribution of gas in a 3-dimensional room. And we have the gas, and we're assuming that this gas is at equilibrium. And so the velocity probability going in the x direction is going to be independent of the velocity going in the y direction, is going to be independent of the velocity going in the z direction. Do you agree with that? That's an assumption which kind of makes sense. There's no wind blowing or anything. It's all settled into thermodynamic equilibrium or some such thing. But the other thing is that this density function, however it is, has to be the same independent of the coordinates. So if you have x and y and z like that, then it should be exactly the same as the distribution of x, y, and z like this, right? There's nothing in the room that sets the coordinate axis of x, y, and z. You can choose the x, y, and z to be anything you want to. And even then, they have to be independent of each other. So this means that the x t1, t2 must also be a function of the function of just the radius of how far you are from whatever point you're looking at. And so there was a 19th century genius that looked at this, and he thought, you know, these are the two criterion that we have to have. Number one is that they have to be independent. So the density functions have to be a separable function, number one. Number two, they're independent of whatever axis, whatever orientation of axis we choose. So therefore, they have to be spherically symmetric. And then he went about and he proved that there was only one function that was that the product that could be expressed as a product that was also spherically symmetric. Does anybody know who that person was? You've heard his name before in relation to something else. The person that did that, who was just a genius, was John Clerk Maxwell of Maxwell's equations fame. And what he showed was that, yeah, you know, you're going to have e to the minus, say alpha, say t1 squared plus t2 squared plus t3 squared. And then there's going to be a constant in front. So this is going to be the PDF. Because can you see, this is going to be equal, this is a separable function, isn't it? This is equal to e to the minus alpha t1 squared, e to the minus alpha t2 squared, alpha, and plus it has spherical symmetry. And just by these two properties, and I look back historically and I think this guy was a genius. He proved that this was the only solution that met these two criteria. And does anybody know what this is called today? It's called the Maxwell-Boltzmann distribution. So if you see the Maxwell-Boltzmann distribution, you'll see that indeed this is the case. But this was figured out by Maxwell just from like a little pinch of knowledge about what was going on. You wanted something spherically symmetric, number one, and number two, it was symmetric. So I think that was just historically genius. Okay. So the proof, here's the separability theorem. We've talked about separable functions. We've talked a little bit about some of the applications. Here is the interesting thing. If you have a separable function, are you ready? Then its Fourier transform, a separable function means the product of one-dimensional functions. If you have a function which is the product of one-dimensional functions, then its Fourier transform is the product of the one-dimensional Fourier transforms. If you're like me when you first look at this and said, hey, wait a minute, hold your taters. If you multiply in the t domain, in the frequency domain, you convolve, right? What happened to that? Well, it turns out it isn't applicable here. You have to multiply in the same variable. What this means, for example, is that the sinc of t times the rectangle of t, t2, say, for example, this has a Fourier transform of the Fourier transform of this. What's a Fourier transform of this? It's a rectangle function, right? And what's a Fourier transform of this? It's a sinc function. So therefore, if you have a separable function, all of the knowledge you know about one-dimensional functions comes into play. You can simply borrow from all of that. And the proof is really, really simple. If we have a multidimensional transform, and I'm going to write it out in longhand. There's the multidimensional function, which we assume is separable. It can be written as a Fourier or it can be written as a product of one-dimensional functions. And then the Fourier transform kernel is as follows. So I've simply taken the shorthand notation for the Fourier transform and written it out in longhand. Is that okay? So x of t, if it's a separable function, Fourier transforms to this. Well, notice I can take these and I can break them up into individual integrals, can't I? Once you see this, you go, well, of course. This proof gives me writing cramps. You see what I've done there? I just shuffled integration limits. That's all. And when can we do this in Fourier analysis? Always, right? Don't worry about it. And you can see that this is equal to x sub 1 of u1. The second integral is equal to x of 2 of u2. And then the last one is x sub n of un. So I'm assuming you're all familiar with this pi notation, right? This is the product notation. Everybody's seen this before? Okay. So the product of a bunch of one-dimensional functions, Fourier transforms into the product of the one-dimensional Fourier transforms. And again, this allows us to dip in the well and go back to our one-dimensional Fourier transform mastery and use the one-dimensional Fourier transforms to good use here. Now, it turns out that most images, most two-dimensional functions are not separable. They occur quite a bit, but they're not separable. For example, if you took my image and you made a gray level image out of it, you ran it through a black and white filter, my image would not be separable, wouldn't it? Would it? You couldn't take one function and smear it this way and another function, smear it this way and get me. I hope not. So therefore, most images are not separable, but nevertheless, this is a good tool to have. But the other thing is this extends to summations of separable functions. Let's take a look at an example. Here on the top, we have a function. Let's see. I have to move my. We're not moving. Okay. Okay. Here we have a function, and I'm going to put this behind. Here we have a function which is 1 inside the shaded box and it's equal to 0 outside the shaded box. Is that okay? Now here's the point. This function is separable. This is equal to a smear of a rectangle function going this way and a smear of a rectangle function going to this way, right? This function down here in the third quadrant is also separable. So we can apply the separability theorem here if we include linearity. We simply have to compute the Fourier transform of one separable function and add it to the Fourier transform of the second periodic function. Does that make sense? And so this is what we do. And the math is here. You can go through it. This is a rectangle. Each one of these rectangles, Fourier transforms to a sinc, and because they're shifted, there's an e to the j shift in the Fourier transform, right? And so this is what happens. This is the representation for both of them. If you use the plus, you get the rectangle in the third quadrant. If you use the minus, you get the rectangle in the first quadrant. And this Fourier transforms to this, and if you add them together, well, you get you get this as the Fourier transform. So we have used the separability theorem. And why do we get this cosine here? We get the cosine because we get a e to the plus j times e to the minus j, right? When we add the two together. And so that e to the plus j and e to the minus j combine together using Euler's formula in order to give us this cosine on the bottom. So therefore we have applied the separability theorem to an example of something which isn't separable but can be expressed as the sum of separable signals. Now, what is interesting is that any image can be written as the sum of separable images. And if you allow an infinite number, or even in a discrete case of a finite number, you can take any image and you can express it as the sum of separable functions. And so this is always the separability theorem in that sense is always applicable. The problem is that you don't have the time to do that decomposition into all the separable functions and do the one-dimensional Fourier transforms. But it is possible. It is possible. Again, all multidimensional signals can be written as the sum of separable functions. But that sum can be over a very, very large number of separable functions. So my image that you're seeing, if you made it into black and white, and you were to analyze it, you could express my image as the sum of separable signals and apply the separability theorem. So it is something which comes up, which is very interesting. This is the generalization of the idea of separability into higher dimensions. So if x of t is equal to the summation over a bunch of separable functions. This looks like hieroglyphics, doesn't it? But it's very useful. So x of t is equal to the summation of separable signals. Then the Fourier transform is equal to the summation of the separable signals. And you only have to do one-dimensional Fourier transforms. That's the cool part. You only have to do one-dimensional Fourier transforms. So here I'm assuming there's an infinite number of separable images. That isn't, again, that doesn't apply all the time. But, well, it always applies, but it's not practical to break it down that way. But this is a very useful way of thinking about the Fourier analysis. So the separability theorem in practice is an easy way to use one-dimensional Fourier transforms to our advantage to do multi-dimensional Fourier analysis. And there is no one-dimensional Fourier transform counterpart to this. Now, next time we get together, we're going to look at something which we haven't seen before either. we're going to look at the Fourier transform of circularly symmetric figures. What is, for example, the Fourier transform of a circle? This turns out to be incredibly important in acoustics and far-field sort of applications. And if you've ever run a coffee cup, a styrofoam coffee cup across the table, and you saw those concentric rings, you will see Bessel functions. And the Fourier transform of circle function does turn out to be Bessel-y sort of functions. And we will talk about that, that next time. Then what we are going to get into is we're going to apply our work in multidimensional Fourier analysis to, first of all, multidimensional Fourier series, multidimensional sampling. We will look at reconstruction of images through tomographic projections. You've all heard of CT scans where you take projections of a person in a number of different directions. We will go through the mathematics, which is beautiful in terms of Fourier analysis, of how you're able to reconstruct the original signal from a bunch of transforms. And we'll go into some other interesting applications. Don't forget, some of this stuff might seem kind of esoteric, but we're going to apply it to some very real world problems and real mathematics in real life. Any questions at all? When there are no questions, I know that I've either been incredibly clear or incredibly opaque. I'm not sure which one it was. I hope I've been terribly clear. So if there's no question, we will see you Thursday, and I will try to put up some homework questions I'd like you to look at so we can discuss next Thursday. And then a week from today, we can do kind of the coin flipping and choose time to work problems. So any more questions at all? Okay. Thank you, gentlemen. Enjoy your time, and remember to inhale only when necessary. Okay.
Thank you.
Bye.
Thank you.